today's lecture because we're missing some juniors in action and so on and so forth. And we started off with this small Quizlet right here, first question. Like so. It's a 30-second Quizlet because the answer is really simple. Everybody out loud, what is it? 4. Exactly. So what theorem guarantees that value?
Did you get 100 back?
Well,
Please.
All right, I'll give you all 2 points out of 2.
Yes.
Now let's unpack the squeeze theorem a little bit because Earl was saying he was confused by it. The picture is that we have a function f. Let's do that in black here. Hello, Tiffany. And we are going to have a value c. And for whatever reason, it is hard for us to find the limit as x goes to c of f of x. But it is easy, for whatever reason, for us to find the limit as x goes to c of 2 bounding functions. One of them is going to be the upper bound h, and the other one is going to be the lower bound g. And what we can see is that f of x is squeezed between these two. So we are going to have as our first condition, if f of x is between h of x and g of x, that's our first condition. And then our second condition is going to be, and if I happen to know, I just happen to know, that h and g go to the same limit, bless you.
Thank you.
And let's call that limit L. Then it must be the case that f of x is squeezed to the value L as well. And the picture that we have here is that all 3 of these, you guys know what a squeeze play is, like in football, right? You've got somebody here who's got the ball and 2 people come from opposite directions and boom.
Well, then they fall down.
Isn't it like bang heads?
A lot of that happens in football. Welcome to head injuries. And so the squeeze play is happening here as well. H, G, and F are all squeezed to the same value right there at C. That's the spirit of it. Now you probably had some questions that were confusing. So what question do you have?
It's probably going to be more complicated than this first. And then, when is this going to happen? Like,
That's a great question. Today we're going to spend all of our time on 2 special limits. And the first one is going to be on the squeeze theorem. Yes?
So we're using less than equal to that. What happens if it's less than? It's equal. It's not equal.
If less than occurs, the result still holds. But it is less. But in that case, we would be weakening the theorem by taking out the possibility that they could also be equal. We would have a smaller class of functions that we could use the squeeze theorem for.
But why would it still hold? It would be close to that.
No, actually, the limit would actually be equal to, and the reason for that is that your limit L here for this guy would now be what is called a greatest lower bound for the range of H and the least upper bound for the range of G. So clearly I don't want to go there, right? But the result would still hold, but we would be removing some functions from our possibility. In particular, we want to keep this because very often our H and G are going to be continuous functions that actually equal each other at the limit point that we're talking about. Okay. Let me just, Peter, to answer your question, let's suppose that I changed my 2 bounding functions like this. like so. So I changed my bounding functions, but notice that each one of these bounding functions is an alias for the original functions that I had. Cancellation will get me there. So now, these two functions are not actually ever equal to each other. Both of the graphs have a fold right at x equals c, but I can still take the limit as x goes to 0 of 4x plus x cubed over x with cancellation. Equals 4, etc. Okay? So, why did that work out? Well, it worked out because notice that in our original statement of the squeeze theorem, we have less than or equal to, right? So that includes the case where this one is less than that one is less than that one. Right? Less than or equal to includes both possibilities. It was a good question. It was a conceptual question. He's worried about the fact that these two functions are coming together in the limit, and yet right at the limit point, neither one exists. Does that still squeeze? Yes, it still squeezes. Good? Good. Often students will ask, and I wonder if this was Earl's question, that he thought it was going to be more complicated, how do you find the upper and lower bounding functions? Is that what's bothering you? Yeah. And the answer is that at our level, Calc 1 level, they will usually be supplied to you, just like I did in this model. Very rarely we will have to hunt down our own bounding functions, but that is a rare circumstance. And one of those two, really is only going to occur in kind of two cases. And one of those cases I will share with you right now, and then we'll get to today's lecture, which will cover the other case as well. Let me show you one case where a student might have to come up with his own bounding function. This is a really crazy function, and if you graph it on a small window size, you will see that cosine of 1 over x does this. Like that. It goes crazy.
Do you want to draw that?
Yes, it goes like this. And it's kind of normal out over here. And so the question now is, what is this limit? I look at that, none of my limit properties apply to it. I can't do product rule because the limit as x goes to 0, cosine 1 over x doesn't even make sense. So, what can I do? Well, I consider maybe squeeze theorem would help. And I consider that the function cosine 1 over x is trapped between -1 and 1. Because that is the, what's our R word for this here? The range of the function of cosine. So again, with the fact that cosine is trapped between -1 and 1. And then I observe that if x is greater than 0, or for x is greater than 0, then I can multiply through by x and find that this is true. Now, I required that x's be greater than 0 because if x is less than 0, what do I have to do with the inequalities? I have to flip them, right? So I'll come back and handle that in a second. And now I've got bounding functions, and lo and behold, as x goes to 0, both of my bounding functions go to the value of 0. Therefore, the interior function goes to 0 also. But that only works for x is greater than 0, so I have to come back and I have to take the limit from the right only. What about x is less than 0? No problem. If x is less than 0, then I can still multiply through by x, but I have to reverse the sense of the inequality. No problem. Trouble?
No. Well, how did you get from -1 to x?
Oh, I multiplied this equality through by x.
Oh,
Yeah.
I was just like
Whoa, where's that? Yeah.
Okay.
And now the limit as x goes to 0 from the left, because x is less than 0, of negative x, is the same as the limit as x goes to 0 from the left of x, which is equal to 0. And therefore, the limit as x goes to 0 from the left of x cosine 1 over x must be 0 also. And since the limit from the right is 0, and the limit from the left is 0, what has to be true? The
limit of the middle one.
Yes, thank you. He's learning not to use the word it. Because the word it is too vague. Yes.
I still don't understand, like, how did you get negative 1 is equal less than, like, the thing in the first place?
What is the range of the cosine function?
1, negative 1, but we got like 1 over x.
No. Because 1 over x is going to be some number, and when I plug that number into cosine, cosine is going to spit out a value between negative 1 and 1.
Right.
Yeah. Yes. Okay. Now, let's do the main story for today. I believe on Edmodo, I have a document for you called 2 special limits. Go ahead and pull that up at this time. And the reason I provided this document is so that you can do a little less writing, a little bit more watching for today. I want your brain to be able to.
Hey, Mr. King, are we trying out these quizzes that we did?
No, I'm just going to give everybody 2.
Okay.
Let me make sure that it's actually on Edmodo. If it's not, I'll put it up real fast.
What's it called?
It's called 2 special limits.
Is it in folders? It's
It's out there? Okay, let me put it up real fast so that you have it. Okay. 2 special limits. Download. Edmodo. Pink. Oh, silly. AB. Pink. Okay, now you should be able to have it. Just go ahead and refresh, and you should be able to pull up this document right here. Our goal for today is to be able to prove 2 special limits for you. And one of those special limits is very famous, and you may have already discovered it. And that is that the limit as theta goes to 0 of sine theta over theta is equal to 1. If you've not already discovered this, let me invite you to get your calculators out at this time and prove that for yourself. Not prove it for yourself, but give yourself strong evidence for it by taking a limit, evaluating the limit from the calculator. So do that at this time. On your calculator, if you graph on the window -5 to 5 by -2 to 2, then your graph should look something like this. And if you look very carefully, it has a hole right at x equals 0, which is not surprising because you can't divide by 0. However, when I try tracing, get x values, let me actually do this live so you can see it. My calculator. And y equals.
Teachers, pardon the interruption. It's time for our tutors for the last name K through O to record the sample for their tutors. All tutors K through O. Don't forget your form.
Okay, I'll set my window size -5 to 5 and when I do, my graph goes like this. Okay, and so I hit trace, and somebody give me a good x value to try. Notice that when x is 0, y doesn't exist. Somebody give me a good x value to try. 0.001. And lo and behold, y is 0.9999983. That's how about 1? And I've tried a positive x value, but now I need a negative x value. Give me one.
Negative 0.001.
Exactly so. And lo and behold, once again, y is 0.9999983. In other words, how about 1? So our calculator is giving us evidence, strong evidence, that our limit should be 1. But strong evidence is not mathematical proof. And so we actually need a proof that this is so. We're going to use the space time to do that. So today, I'm going to take you on a little bit of a tour of some of the trigonometric notation. You guys know that the unit circle here is the basis for our trig functions. We start with a unit circle, in other words, a circle with radius of 1, and we identify this point as cosine theta, comma sine theta. The x-coordinate is the cosine, the y-coordinate is the sine. Well, because this is cosine theta, the x-coordinate is cosine theta, that means that if I drop a perpendicular, then the length of this segment here has to be cosine theta, and the length of this segment has to be sine theta. Right? So this gives me a small triangle. 1 cosine theta, sine theta. And if I now go all the way out to the edge of the circle, and I draw myself a tangent to the circle, and I have that tangent intersect the secant of the circle, right here, then I get myself a larger triangle, whose side is tangent, and whose hypotenuse is secant. So this is a larger triangle. Now I want to say a word about these names here, because you'll notice that I use the word tangent in the sense of geometry, in that it touches the circle. And what an interesting coincidence that it happens to have the same name as the trig function. And I also use the name secant here for the line that cuts through the circle. That's in its geometric sense. And what an interesting coincidence that it has the same name as the trig function. Well, it turns out that's not a coincidence at all. The Arabs were the ones who invented trigonometry. They did so in about the 8th or 9th century. And I think I mentioned to you that they did so because they needed to be able to navigate along the Mediterranean. Did we talk about this at all?
Yeah.
Yeah, I mentioned it? Yeah. And so they used little models of triangles, similar triangles, in order to model distances based on angles. That's what they were about. Give me an angle, and I can tell you a distance. That's what they wanted to do. And so these models were based upon the circle, as I've mentioned right here, just like this. And they used the Arabic terms for the various segments. So they used the Arabic term for the tangent segment. They used the Arabic term for the secant segment. And they used the Arabic term for what we call the segment that cuts across a circle like that on the inside. A chord. That's right. They used the Arabic term for chord. And in at least classical Arabic, the term for chord was based upon the idea that this thing looks like a bow. And so they used the Arabic word for bow, which was jibah. Just, there it is. Now something interesting and funny happens. Because they are trading, the Europeans now pick up on this trigonometry idea and they say, hey, we can do that too. And so they began to write books of trigonometry. How do you figure out distances from angles? This is a really clever idea. And between the Arabs and the Europeans, I don't know which, they eventually came up with trigonometric tables for every like 5 degrees or so. So the sine of, or the tangent of 5 degrees is this, the tangent of 2 degrees is that, etc. Here's the problem. Classical Arabic, and I think probably modern Arabic also, when written, does not have vowels. Just as Hebrew does. Hebrew as it is written does not have vowels. You can add vowel connections. You can do that in Arabic, and add vowel connections above and below.
Pronounce things without vowels.
It's not that they don't have vowels, but the written language, at least when it's written quickly, doesn't have vowels. So the way that this would be written would just be jibah. And you just have to know that it's jibah. Well, unfortunately, the person who translated it did not know that it was jibah. And he translated it as if it were jaib, which means cavity or hole, or in the Latin, sinus. In Latin, what? Sinus. Something like that. As in like your sinuses, as in the holes in your cheeks that let your voice resonate. And so as a result, the bow, or the chord segment, was translated as if it were the hole or sinus segment. And we ended up with sine as a mistranslation of the original Arabic term for chord. Yes?
What, do you know what jiva would be? Like the bow, like what that is in Latin, more or less? Like,
No, I don't. It would just be a short bow.
I feel like, wait, 1 second, I think I know.
All right, you find out. You could try to rename it, but I think sine is here to stay. All right. Now, what about the cosine? Well, the part of the cosine, which you may have noticed also is present in cotangent and cosecant, comes about because the two angles of our triangle are complementary to each other. So that if this is the angle theta, then this is going to be the angle 90 degrees minus theta. We call that the coangle. And so you can see that the sine of the angle is the same thing as the cosine of the coangle. They have the same relationship to one another. And so for that reason, cosine is really short for complementary sine. It is the sine of the complementary angle. Yes?
Very interesting.
Uh-huh.
Arcu.
Arcum.
So that might have been called
Arc.
Arc.
Yes, interesting. All right. So that's where we are. But now, you guys are familiar with secant and tangent meaning something else, right? It's not the length of the outside segment. It's what? If I say tangent theta, you think what? Sine over cosine. Here's our payoff. Our diagram shows almost all of the trigonometric relationships that you need to know. Why? Take a look at these two triangles. They both have the same interior angle theta, and they're both right triangles. Therefore, they are what? Two triangles, two angles congruent. Similar triangles to one another. So their sides are in proportion. So immediately, look at the ratios that I get out of this. Sine is to cosine, just like tangent is to 1. Boom. Isn't that cool? But wait, there's more. 1 is to cosine. 1 is to cosine, just like secant is to 1. Boom. And if I were to draw myself a triangle for the coangle, it would be right here. Then I could also get relationships for cotangent and cosecant, but I shall not do that at this time. But wait, there's more.
Explain that, like, stuff like sine over cosine. I still don't understand.
These two
Part of the
triangles
eruption, all of the remaining
have the same angles, therefore they are similar. Therefore their sides are proportional. What's the sides? What are the two legs here? Sine over cosine is the same as tangent over 1. 1 over cosine is the same as secant over 1. Yes.
And then 1 over tangent is the same as cosine over sine.
And 1 over tangent is the same as cosine over sine. Yeah, that's right. That's exactly it. But wait, there's more. Because if I now consider that these are right triangles, what is the thing that we all know and love to do with right triangles? Pythagorean theorem. Let's do that. Sine squared theta plus cosine squared theta equals 1. Tan squared theta plus 1 squared equals secant squared. Boom. Pythagorean identity straight off the triangles. See it? There's much more to this. I'm not going to go into it at this time, but I want to spend some time so that you can see how these triangles contain a whole lot of your trigonometric knowledge right there. So that if you're ever lost or confused about trig stuff, often drawing this circle can help clarify some things. Okay? Now, let's get to our main story. What I propose to do is to use the squeeze theorem to prove this limit right here. And the proof is found in the pages that follow, so I do not want you to spend a lot of time writing down stuff. I just want you to listen for now. I'm going to replicate the diagram on the page here and go. Okay. What I'm going to do is I'm going to draw the inside and outside triangles as we did for our unit circle. And when I do, then as we did before, I get sine theta here, and I get cosine theta here. And I get tan theta on the outside and 1 on the outside. And now what I'm going to do is I'm going to compute the areas of those two triangles. And I'm also going to compute the area of this shape on the inside, which is a little pi wedge or a sector of the circle. All right, so let's do the areas of the triangles first. My inside triangle has an angle of theta, and it has a side of cosine, and has a side of sine, and it's a right triangle. So its area, let's call that little triangle. Actually, I'll just use a little triangle shape for it. Is 1/2 of base times height, which is 1/2 of the base is cosine theta, and the height is sine theta. Is everybody with me so far? Meanwhile, the outside triangle has a height of tangent theta, and it has a base of 1 because it goes all the way out to the radius of the circle.
Wait, why doesn't the first one have 1, 2?
Because we dropped our perpendicular from this point. Good question. That's a good question. How did I think of this? Is what you're really asking. What motivated it? Not sure yet. So just go with it for a moment.
I also have a question. Is the top, is that a sine x or sine t?
This says sine theta, but it's really badly drawn out. Written. It's right there in that diagram.
Oh.
You scroll down. I've written all of this out, so you should not be copying this. You should be listening. And thinking good questions like your good questions that you had before. So the area of the large triangle then is going to be 1/2 of base times height, which is 1/2 of tan theta times 1. So I've got these two. Now what about the area of the sector inside? I promised I would deliver on that as well. The area of sectors is not commonly taught in geometry, but it should be. Were you taught that in geometry, the area of the sector? A sector is a pi wedge. It's a portion of a circle. No. You were a little. Okay. All right. Well, let's go over it. It's not a hard thing, but we need it. So we'll do it. We're going to think about the sector as a fraction of the circle. So the sector is a percentage or a fraction of the entire circle. What's the area of the entire circle? No? Pi r squared, right. But your units be your guide. It has to be the square one, because it's square units for the area. But the radius of a unit circle is simply 1, right? Actually, let's keep it at pi r squared for now, so we'll get a general formula for areas of sectors. So we're going to think of the area of the pi wedge as a percentage of that. How do I compute the percentage? Well, the angle that I have is theta. The whole distance around, in terms of angles, is 2 pi. So this is the fraction or percentage of the circle that we're talking about. If I have a quarter circle, this angle would be pi over 2, and I would get 1/4 as my fraction. If I had a half circle, my angle would be pi, and I would get 1/2 as my fraction, and so on and so forth. So if I now multiply that by the area of the circle, 1/2 of pi r squared, then my pi's cancel, and I get the general formula for the area of a sector or pi wedge, which is 1/2 of theta r squared. The r squared, obviously, because we're talking about the area of the circle, and the 1/2 theta, because theta is the fraction out of 2 pi. Are we good? Okay. Let's apply that to our sector. Our sector happens to have a radius of 1. So its area is simply 1/2 theta. This is our setup. This was the hardest part about all this. Now we're ready to make this relevant. If you look, it is intuitively obvious that the small triangle is always inside the sector, and the sector is always inside the big triangle. And that means that my areas here, here, and here are always strictly ordered. The small triangle is always less than or equal to the area of the sector, which is always less than or equal to the area of the big triangle. And now we have a setup for squeeze theorem. This area is 1/2 cosine theta sine theta. This area is 1/2 theta. This area is 1/2 tan theta. Isn't that cool? Now we're not there yet. We're going to get there. The rest is just a little bit of that. Okay. And what I'd like to do is to simplify this. Does anybody see some obvious algebra that should happen here?
Times everything by 2.
Times everything by 2. Multiply everything by 2. Cancel it with 1. But I'm going to simplify it even further. I'm going to divide through by sine theta.
Cos.
It's gonna be
Plus sine.
1/cosine. 1/cosine, right? Okay. Now, when I divided through by sine, I didn't check something. In order to keep my inequalities the same, what has to be true? Yeah.
Theta does not equal 0.
Not only does not equal 0, it actually has to be positive. It has to be greater than 0. In which quadrants is sine theta greater than 0?
First and second.
The first and second quadrants. So actually, this inequality we've got right here is only valid for thetas that are greater than 0. I'll have to fix that in just a minute and consider thetas less than 0. In other words, right now I'm only considering what happens in quadrant 1. I'm going to have to come back and consider quadrant 4 in just a minute, because theta could approach 0 from here. From one. Okay. And now that I've got this, I'm ready to take a limit. Since the limit as theta goes to 0 of cosine theta, don't work too hard at this. What's cosine of 0? 1. It is. It is cosine a continuous function? Think about the graph. Yeah, it's continuous. So therefore its limit is 1. And the limit as theta goes to 0 of 1 over cosine theta is 1 over 1, which is 1. Therefore the two outer limits are the same. And therefore the limit of the inside must also go to 1. Well, this is almost what we want, but it's upside down, isn't it? That's okay. That means that the limit of the reciprocal is the reciprocal of 1, which is still 1.
Wait, why? I lost.
Where? Which part?
Why is that backwards?
Well, I wanted to prove that the limit as theta goes to 0 of sine theta over theta is 1.
Oh, okay.
So it's upside down from what I want. So that's not a problem. I take the limit of the reciprocal and say that's the reciprocal of 1. But thetas were positive here, so I'm approaching 0 only from the right. What about from the left? Well, I could set all this up and do it all again from the left, but I'm not going to. Instead, as I go from the left, I'm going to appeal to the fact that sine is an odd function. And I'm going to pull off a substitution. I'm going to let w equal the opposite of theta. So that if theta goes to 0, then w goes to 0 also. But if theta is going to 0 from the left, then w is going to 0 from the opposite direction. And theta is negative w, and so I can replace just like that. But since sine is an odd function, out comes the negative sign. Boom. Cancel. And now I have the exact same limit as I had right here, just with a different variable. What's its value? 1. And so the limit from the left is 1. The limit from the right is 1. What is the value of the overall limit? 1. What a profound thing. Now, all of this is written down in your document, so I'm not going to take some time to go over it. I do want to give you the big picture. Big picture. 3 areas, squeeze theorem. And that's it. Isn't that a nice big picture? We have our unit circle, 3 areas, squeeze theorem. Do you have to be able to do this proof? This proof, I would say, is a good bonus question. Kind of preserve this.
I see.
But the second special limit is much easier and is a valid thing for me to ask. In only 3 minutes, I'm going to prove to you our second special limit using the first one. So far, I have proved that the limit as theta goes to 0 of sine theta over theta is equal to 1. We're going to use this fact several times in this course. Now my second claim is that the limit as theta goes to 0 of 1 minus cosine theta over theta is equal to 0. If you check the form on this limit, you can see that the form is 1 minus 1, which is 0 over 0. And so, theoretically, there should be a common factor that I could cancel, but it's not obvious. when we did the rationalization, the way that we found our common factor was to rationalize. I'm going to do something very, very similar. I'm going to multiply top and bottom by the conjugate of 1 minus cosine theta, which is 1 plus cosine theta. And when I do, in the top, I get 1 minus cosine squared theta. In the bottom, I get this expression, which I am not going to simplify, because I know that I'm looking for some factors here. Do you know another name for 1 minus cosine squared theta? Aha! And now I'm going to be exceedingly clever, because sine squared theta means sine theta squared. In other words, sine theta times itself. And here's where I'm going to be clever. I already have a limit as theta goes to 0 for sine theta over theta. So I'm going to use that limit to peel off a factor of sine theta over theta, leaving me with some other stuff. And I don't really care what that other stuff is, as long as it's good. And now I can use the product rule for limits. And let's examine each limit separately. This limit, we already know the value of. What's its value? 1. So this limit goes to 1. What about this limit? This limit turns out not to be hard. Just use the quotient rule on it. Sine theta goes to 0. 1 plus cosine theta is going to go to 1 plus 1 is 2. 0 divided by 2 is 0. So that I get 1 times 0 for my limit, which is 0, as advertised. This proof you should definitely be able to do. And the spirit of it is rationalize. And when you rationalize, use your identities, it all pops out. Practice doing it a couple times tonight. Or sitting board in English. Wait, did I say that?